The first speaker is Jacek Tafel. So actually Jacek was technically my supervisor of my PhD. When I met Professor Trautmann for the first time, Professor Trautmann introduced me to Jacek and Jacek to me. Well, actually we knew each other earlier, but he introduced me Jacek in his new role as my additional supervisor. So technically, I was working with Jacek directly, and maybe Jacek reported to Professor Trautmann if we made any progress. So today, Jacek will, Professor Tafel will tell us on the Penrose inequality to the perturbed Schwarzschild.
Thank you very much. I know Jurek since his studies, so many years. We not always talk about science, but often we talk about skiing or climbing, things like this. So I wish Jurek many years of fruitful activity in science, but also in sports. Okay, so Penrose inequality. Jurek is my PhD student, and in fact, this subject we initiated because I thought that it should be relatively easy to find counter examples to the Penrose inequality. But instead of this, we proved this inequality for some class of mathematics. So the Penrose inequality is simply a relation between total mass of gravitational configuration and the surface area of the horizon. And for the curved horizon, it is obvious, and more obvious when it is for the Schwarzschild solution that the angular momentum A vanishes, then this inequality is saturated. Now, a stronger version of this inequality is that the square of the total energy minus square of total momentum, linear momentum is bigger than surface plus square of the angular momentum. Yeah? So this is, of course, satisfied for curved solution where the angular momentum is non-trivial. Now, and in fact, we this is obvious for the curved solution, but because of this expectation that in the infinite future, perhaps every configuration with internal horizon will tend to the curved solution, we can expect that this inequality will be satisfied also on some in earlier time. It means on say on some initial surface, because later on we will get lower energy and bigger area of the horizon because of black hole thermodynamics. Yeah. So if it is satisfied in infinite future asymptotically, then perhaps, or it is not sure because of course this is not strict theorem, but one can expect this to be satisfied on any initial surface in G. So the challenge is to prove this inequality just starting from equations on initial surface. On initial surface we have two data. We have metric tensor and the symmetric tensor, which plays the role of the exterior curvature later on. So, and we have momentum constraints, which are linear in curvatures, and we have Hamiltonian constraint, which is quadratic in the curvatures. Here, H prime is the phase of the curvature tensor K I J. So, if Penrose inequality is satisfied, it should follow from constraint equations. And what about horizon? For the horizon, we just, here we define horizon as a marginal outer traffic surface. It means it is compact surface with vanishing expansion of null rays, of outgoing null rays, and this condition of this vanishing expansion of this vanishing expansion means simply this equation. This is the equation for vanishing expansion. Here we have the exterior curvature, normal part of the exterior curvature. We have also mean curvature of the two-dimensional surface. Imagine we have three-dimensional initial data on initial surface. On this surface, we have another surface, two-dimensional surface, which plays a role of the horizon. And we calculate the mean curvature of this two-dimensional surface. This is H. And we assume that we have this relation between curvatures and on the surface. So physically, it means that this outgoing null rays they don't they converge. Yeah? There is no.
So capital H and small h are the coordinates of null mean curvature of the two surfaces.
Yeah. Small h is two surface and capital
H
is three
two
surface.
surfaces.
Now, in the conformal, we will consider conformal approach. Yeah? I convert the constraint equations into conformal language. In this language, we assume that we start with metric Gij, and then we consider conformal metric. We introduce a field which we are going to obtain from equations, a field psi, conformal factor, and also for there are different methods, but say we introduce the traceless symmetric tensor A and H prime, which is exactly the trace of the left-hand side. Yeah? So we have here we treat this basic metric Gij as known, and we try to derive psi A and H prime from constraint equation. And the momentum constraint is relatively simple, but already non-linear because of the right-hand side. The constraint becomes so-called Lichnerowicz equation, which is more complicated. So we have squares of curvatures on the right-hand side, but we have also nasty powers of this conformal factor psi. R is the Ricci scalar of the metric Gij. Many of you know this equation. And now what about this condition of vanishing expansion on the horizon? Now it becomes a boundary condition for this function psi. So this is the normal derivative of the function psi on this two-dimensional surface which plays role of the horizon. So this is the Neumann type boundary condition on psi. It's not exactly Neumann because psi is also in all other places, but this is condition for normal derivative of function psi. So these are all equations which can serve to derive Penrose inequality. There's nothing. Now, what about existence of solutions? This is subtle problem, and there are not so many existence theorems. Most of them refer to the case when h prime is equal to 0, so-called maximal data, or non-maximal data, like this is more difficult. But here I will not, I will simply assume that solutions exist. I don't, okay, so our strategy is the following. We try to, we start from Schwarzschild, we add some extra exterior curvature, and we try to see what happens with the Penrose inequality. Schwarzschild solution, which means conformal flat metric, which of course allows us to for much more exact calculations. So assume that we have this basic metric is simply flat, and the surface is sphere with respect to this flat basic metric. It has some radius. Now, if the exterior curvature is exactly 0, then we simply get the conformal factor, and everybody knows that this factor is the Schwarzschild initial metric, and with after change of coordinates, r is different from r prime, we get usual form of the Schwarzschild metric on T for constant. And the inequality is separated. So what we do is we assume that there is a small parameter epsilon, and curvatures are at least of the order of this epsilon. So this is the main part of the exterior curvature. This is the main part of the trace of the exterior curvature. This is trace part. So it doesn't matter. These are say the main parts, and these main parts are of the order of epsilon. And epsilon is small. So we expand the conformal factor into series. This doesn't depend on epsilon. This is first power of epsilon, and so on. So the usual approach with small parameter, and we write equations again. So approximate equations now are much better because the momentum constraint is much better because psi naught is long. So this is linear in curvatures, which is always good for us. What about the second Hamiltonian constraint, or the Lichnerowicz equation? The right-hand side here contains only known function C0 and squares of curvatures. So assume that we are able to solve this equation with respect to B, I, J, and D. This is undetermined system of equations. We have only 3 equations, and we have 6 unknown functions. But still, this is linear, so perhaps we can solve it in terms of arbitrary functions. Then we can substitute solutions in the right-hand side, and we can try to find function psi. If we can solve this equation, of course, we can simply compute everything. The final total energy, momentum, and also surface area of the horizon after the conformal transformation. But of course, the problem is with solutions, because you can imagine that we can, solve this equation, but there are several free functions. Then you take squares of that, and nobody will find exact solution. Perhaps we can express the solution in terms of some integrals, but they are not very helpful to estimate energy or momentum and so on. So it's not, even in this approximation, it's not easy to get any relation between energy and surface area. So this relation between energy and area should follow from this Hamiltonian constraint, yeah, from the Lichnerowicz equation, because here this equation doesn't contain the function psi, and function psi defines the finite configuration, and so the finite energy and area. Okay, so what about the Lichnerowicz equation? Remember that psi, in fact, is decomposed into psi naught, which simply gives 0, psi 1, and psi 2. Psi 1 is linear in epsilon, the right-hand side is quadratic in epsilon. So psi 1, Laplacian of psi 1 simply vanishes, yeah? So psi 1 is harmonic. Psi 2 is more complicated because it has this source term here on the right. So the crucial thing is how to solve this equation, or in fact how to avoid this equation, still having some formulas for energy and area after the transformation. So I try to simply formally to integrate this equation, but only formally, and to use finite expressions to be able to.
You say only formally because you don't control the falloff of D?
No, this I control. I assume asymptotical flatness, but I simply write some integrals, but of course I don't perform.
But do we know that solutions to the previous solution, they are all of the type that these integrals exist?
Maybe I didn't write this assumption, but in case of the asymptotical flatness, say, I would assume that Bij is like 1 over r squared, yeah? Or less, but some kind of this assumption. Yeah? So integration is performed between the between surface of the horizon up to infinity. So SH denotes the surface of horizon, S infinity is here at infinity. And see, this is obvious, yeah? When we integrate Laplacian, we get boundary terms, these two boundary terms. One of them I simply shifted to the right-hand side, yeah? But what is the term to the left? This is in fact the energy of ADN total energy is related to the integral of the left. If you simply take ADN formula for total energy, you substitute the conformal flat metric, you simply get this energy. Yeah? So left-hand side is energy. So you see, now, so the left-hand side is good. This is what we want. Sorry for this. I wanted to use pointer, but doesn't matter. So left-hand side is proportional to the total energy. So this is what we want. What about the right-hand side? Here is the boundary term, and psi over r is given by this condition of marginally trapped surface. Yeah? So the first term will be boundary term, which will be probably easy to find. The problem is, of course, with this integral, volume integral of squares of curvature, and this is difficult to estimate. But let us leave it in such a form. I am happy that I can get energy in terms of boundary terms plus some volume integral of squares of curvature. Now, what about the surface area? Can we get a similar formula? Yes. The surface area, after the conformal change, of course, the surface area will be psi 4. Yes, psi 4. Okay. I was afraid that this power is not, but it's okay. So we need, so I expand this 4th power of psi according to this expansion of psi itself. So I do expansion up to epsilon squared. So this is a epsilon squared term, and also this one. Yeah? And now psi 1 here and here are easy to find, because this is harmonic function satisfying some boundary condition. Harmonic function in flat space we are able to find, perhaps in terms of harmonic functions, maybe in some other ways, but say relatively easy part. What is not easy is finding integral of psi 2. And here there is a trick. Yeah? We simply take again the Lichnerowicz equation, we integrate it first over spherical coordinates. So here this bracket, triangular bracket here and here means integration over two-dimensional sphere over spherical coordinates. So these are, and we rewrite this in, we have only this radial part now. And we integrate this equation twice to get this integral over the spherical coordinates. In the process of integration, we have two constants, but these constants are completely defined because of asymptotic condition that psi at infinity is equal to 1. So it means psi 1, psi 2 vanish at infinity. And on the horizon, derivative of psi is given by this condition of marginally trapped surface. So we do this, and we get formula which is this one. I am not going to write this formula because too many expressions, but having these two formulas, we can simply write function of defined in this way. So in order to compare the total energy and area of the horizon, we can simply produce such an expression. And from these formulas, which I presented in the previous slide, we get the following formula. And now it looks maybe not nice for you, but look here. H means value on the horizon. So this is boundary value on curvature, integral over spherical coordinates we take on the boundary. So it is easy part. Yeah? Here, psi 1 squared, again, integrated taken on the boundary, easy. What is not easy is this one. Yeah? This is volume integral of some of squares of exterior curvatures with some factors. Yeah? Psi naught is this function with psi itself. Yeah? So what psi 1, this is, I just recall that psi 1 is harmonic function, it satisfies some boundary condition, and this is simply the boundary value of this derivative. Yeah? So here we have this boundary value directly, but we also calculate psi 1 and we calculate this boundary value. So this can be done.
So this m is what? Is something related to E?
M is mass, is radius of this horizon. Yeah? The assumption was that the horizon is related to the two-dimensional sphere in flat space. This sphere has a radius. This radius is m². This radius m² is related to the mass of the Schwarzschild solution, which is perturbed by these curvatures. Because psi naught contains this parameter m. Yeah? Sorry, I didn't write that radius. The radius of the sphere is m². Okay, so the main problem is how to estimate value of this. And now this is positive, this is negative, this is positive or negative. For instance, if for maximal data this is 0, so this term is always positive. But even in this case, we have two positive terms, but one negative, and we still have to show that the positive terms are bigger than the negative term. Yeah? This is not obvious. In fact, as you see here, if we don't use the momentum constraint, then I can always produce any sign of this function here. Yeah, it can be positive or negative. I can do this as I want. So momentum constraints are really needed to prove Penrose inequality or this group. Well, the simplest case, of course, is when we assume axial symmetry, and then momentum constraint. One of them can be easily solved. Solution is given in terms of function omega. The contribution from this part is this is this previous integral, yeah, but now I simply write these two components, squares of them, instead of cosine theta is z. So this is just notation. Now, what is important here, that from regularity conditions, yeah, for theta equals 0 or theta equals pi, we can find that this function omega has the following structure. Right? It must be of this structure. So J here is a constant. In fact, this J has an interpretation of the total angular moment. Yeah? Also called curve solution, we have this formula. It's also true. And because of this, now we can simply plug all this expression to this and this, and you can show that this volume integral here is bigger than square of J divided by 4 mass squared. And because this is only second order approximation in this parameter epsilon, this inequality is the same as we can replace m by surface area factorizing up to epsilon squared. So this will be important in finite formula. Yeah? The other two equations are more difficult, but they are solvable. You can solve them in terms of some free functions. There are two equations for two functions, linear equations. They are not bad. We can solve them in terms. The problem is that if we take any solution, we don't see anything. If we take bad parameterization, we cannot prevent anything. Yeah? So the parameterization is really what is here needed, because we have to estimate this integral. Yeah? Now it is written in terms of all these functions, this integral. I simply tell you that I will not write you exact formulas, but we choose two free functions, x and y, and this function is related to, will be defined in terms of x and y, and this is the best parameterization which we know. It means we can proceed with this parameterization. Function w is defined by this equation. Don't be scared, because the right-hand side is defined in terms of x and y. And here, everything which contains only derivatives with respect to z or angle theta is not terribly dangerous when we use Legendre polynomials description of the right-hand side. Yeah. So this choice is motivated by convenient expression when we make Legendre expansions of functions. So we expand into Legendre polynomials, then we get also expression for this function W. What is interesting here that these are some definite coefficients which depend only on functions, coefficients with the same index n. So index n is everywhere here the same. Now, these are some polynomials. These polynomials are not Legendre polynomial. They are shifted by derivatives of Legendre polynomials. But what is, we are lucky that these polynomials are still orthogonal. Well, otherwise we would fail. Okay, because they are orthogonal, we substitute these expressions in these volume integrals, and we get sum of expressions. Each one is depends only on x and y with the same index. Yeah? So this is a separation of variables. Yeah? Each coefficient in the Legendre expansion is in another expression in this sum. Yeah? So there is no distance. And now, even more, this function here is simply quadratic in function y, and has minimum simply for some value of this function y. And this, I don't write these coefficients, but they are of course definite coefficients. You can calculate this at minimum. So if we know minimum, we know that this volume integral is simply bigger than something. And this something is p squared here. P is one of constants, and this constant is simply total linear momentum of this configuration. Here we have sum over all indices n, and these are h means horizon boundary value of this coefficient 6 and on the boundary. And now we can come back to the relation between x and b, and we find that simply these are boundary values of this function. This function is exactly the function which stays on the right-hand side of this expansion free condition. Yeah? So this is something which already appeared in the very beginning. And now, if we take all what we have, it means this estimation, also this one that is bigger than j squared divided by something. We calculate the boundary terms in this. We simply get this inequality. Yeah? So the difference between square of the total energy minus the area of the horizon is bigger than this plus square of the momentum plus sum of positive terms. So this is always positive or it is zero. And so if any of these terms here is different from zero, it means that Penrose inequality is sharp, is satisfied and sharp. What happens if all of them vanish? You see here is the count from 2. So if all moments, higher moments than quadruple and higher moments are vanishing, then of course we don't know what to do. It means we have to pass to the higher order terms in this parameter epsilon, which may be difficult. And so let me summarize what are assumptions first. We consider axially symmetric data with metric which is conformal effect, and with horizon which corresponds to the sphere with some radius in the flat space. No? We also assume that this calculation, that this perturbed approach is, can be applied. Yeah? So we get a small parameter, and we assume that everything can be expanded, and it makes sense. Okay, so results, the Penrose inequality is satisfied in the order of epsilon squared. Yeah? In generic case, generic means when at least one moment is different from zero. Say
Square root of.
this is our definition for the purpose of this paper. Yeah? For maximal data, okay. So for maximal data, we can also prove Penrose inequality in non-generic. So if all moments, quadruple and higher moments of this X vanish, we really can pass to the third and fourth order, in fact, needed, and we prove the Penrose inequality. In the case of non-maximal data, this seems to be, it seems to be too difficult, and we cannot do this now, but we believe in this. What are perspectives of this approach? I believe that we can include dependence on the angle phi, so not axially symmetric fields. What about other surfaces of horizon which are not spherical? This would be difficult in this approach. First, of course, we would like to do this, but the problem is that we use here the expansion to Legendre polynomials, which are good for spherical surfaces. Yeah? If we change the surface, probably we should modify first the proof in some other language, not using Legendre polynomials. Yeah? Thank you very much.
We have time for questions.
So I was under the impression that Koiskin and Lamin had shown it in the case in the Riemann, that the scalar curvature is positive, right?
Yeah.
So, but if you assume this maximal data, so if the data is maximal, then scalar curvature, but scalar constraint equation is it scalar curvature is just equal to k minus k, so it's positive. So we already know completely general.
No, we don't know. The Riemann and I forgot to tell, of course, the idea of Garrosh and then
Jang.
proved
Jang. The Jang equation.
Inverse mean curvature flow equation.
Sorry?
Inverse mean curvature flow equation.
You know, they assume that the horizon is minimal surface. That we don't assume. So this is the difference.
Thank you.
Are there more?
In fact, there is only one paper or two papers by Malec, Roszkowski, Mars, and Simon, where they consider non-minimal surfaces. I don't know other papers at all.
Okay, if there are no more questions, let us thank you.